Okay, so like we said, the first thing we want to do when we talk about populations is talk about how they're distributed. Population distribution is how individuals are spread out within their environment, okay, compared to one another. Remember, we're only looking at one species. That's what a population is. So the first way, like we said, was random. They're just kind of thrown out there. Some are close together, some are far apart. There's no real pattern to it. A good example of this would be like dandelions in a field, right? Where their seeds are dispersed by the wind, they end up landing wherever they end up landing, and then they end up germinating and kind of being distributed randomly. The second way we said was uniform. Okay, the example I had here was penguins. I don't know if you guys have ever seen the bird colonies, how the birds are spaced so far apart from one another. There's not a whole lot of room, but there's definite even spacing between the individuals. Okay, looks like that. Usually this happens when you have a high population and space is your limited resource. Lastly, you have clumped, which, as you can see, these are kind of grouped together, high density areas and low density areas. Okay, an example I have for that would be ant colonies. Okay, another one would be human cities, how they're close, clumped together. Okay, so once we've talked about dispersal, the next big thing we want to talk about today within populations is growth. Okay, this is kind of the big thing of the day, is how populations grow. This is our big main objective here. How populations change over time is growth. Sometimes you have positive growth and populations are increasing in their size. Other times you have negative growth and populations are shrinking. Now, population growth can be calculated pretty simple. It's just your birth rate minus your death rate. All right? We probably won't do too many math problems that are going to be based around growth, but the general idea is if you're having more births and less deaths, your population is going to be growing. Whereas if there's not as many births and the death rate is higher, your population is shrinking. We'll probably look at a couple case studies with some specific species that are experiencing both positive and negative growth. Now, population growth, because remember we're talking about an area, is influenced by movement of individuals. Some individuals move into an area, maybe because there's more resources. Sometimes they move out of an area. And we just want to be familiar with the vocabulary here. Immigration is when individuals will move into an area, so make sure you underline that you know immigration into, both being with the same letter. And then emigration, individuals moving out of an area. Okay, so like I said, we've talked about distribution, but now we're going to really focus the next few minutes on growth, how populations grow. Okay, so now that we've started talking about populations and growth in a little bit, we want to go into more detail. The first type of growth is called exponential growth, and this is when conditions are perfect. They're ideal conditions and unlimited amounts of resources, unlimited amounts of sunlight, unlimited amounts of soil nutrients. There's unlimited amounts of water, there's unlimited amounts of space and food. I call this la-la land because it's not real, all right? And the big thing we have to remember is that a larger a population gets, the faster it grows. So it's going to start off slow and then it's going to pick up steam. The reason why we call it exponential is because this line here, which shows exponential growth of something over time, the curve is a exponent, okay? The formula for the line is an exponent. And remember how we talked about the larger a population gets, the faster it grows. Well, that's the case with exponents. 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16, and 2 to the fifth power is 32. So it gets bigger and bigger over time. Okay. So let's take a look back at this graph. This shows how the population goes up over time. It starts out slow and increases, it gets faster and faster and faster. So here on the y-axis, our dependent variable would be the number of organisms, and this would be the time. Okay, so as we're watching our populations growing, get faster and faster and faster, and theoretically it would continue on forever. If we had unlimited resources, it would go all the way up into the ceiling and go on forever. But that's not reality. Okay, but that is exponential growth. What we want to look at here is what's called logistical growth. Okay, this is when a population its growth slows down and stops, okay, where it stops growing. The population doesn't necessarily get smaller, but the growth stops. The growth would be zero. The birth rate and the death rate are equaling out. So this is when a population growth slows down and stops after exponential growth. So here's our picture, here's our graph of logistical growth. And you can see this part here, this is exponential growth. And this is usually when there's way more resources than individuals. But after a little while, the growth starts to slow. And it kind of gets to a point where it gets too big. The population is too big for the environment. So it kind of ends up coming down. There's more deaths than births at this point. And eventually it kind of stabilizes. Okay? So there's three main parts to this. There's the exponential growth. There's when the growth starts to slow down. The population is stabilized. Okay? In this model, in our logistical growth model, it incorporates the pressures of limited resources. Okay, we know that there is a finite or limited amount of space or a limited amount of water in an environment. Okay, it's much more realistic. Now, if you look here at this dotted line, I have it labeled as carrying capacity. Okay, what a carrying capacity is, it's the maximum number of individuals an environment can support. Okay, at this point, it can't support anymore. Okay, there's more animals or plants or bacteria or fungi than the environment can hold. So what happens is it comes back down, and eventually the population stabilizes at this carrying capacity. Okay, there's a lot of talk right now. What is the carrying capacity of the world? How many humans can Earth support? Okay, some people think we've passed it. Some people think we are not yet to it. Some people think we're right there. So that's what carrying capacity is. It's the maximum amount. It's like the maximum occupancy of a room. Okay, it can't hold anymore. Anything above that, eventually the population is going to decrease because individuals will die because of lack of resources. Okay, so one thing that does influence carrying capacity is what's called limiting factors. Limiting factors are things that influence growth and limit the growth of a population. For example, there's two types. There's what's called density dependent, which depend on how many individuals are in an area. Okay, the more individuals there are, the more these density dependent factors play a role. Things like space. Okay, when there's limited amounts of space and there's lots of individuals, space becomes a limiting factor, and it'll keep the population down. Another one is disease. The bigger the population, the higher density of the population, so the individuals are going to be closer together, and so diseases are going to transfer easily. Okay, that's a density dependent factor. Okay, remember these are limiting factors, things that limit the growth of a population. The other type of limiting factor is a density independent factor, something that isn't going to matter how many individuals there are. It's just going to end up happening, like, let's say a forest fire. Okay, it's going to happen whether the population is big or the population is small. So just to kind of recap, populations are one type of species. We're looking at the amount of one type of species. They can be dispersed in a number of different ways. They can be spread out randomly, they can be spread out in a uniform way, or they can be spread out in a clumped way where you have a group clusters of individuals. And then we have population growth, which shows how the population changes over time. So, and there's two types of growth. There's exponential growth, where resources are unlimited, and the population gets bigger and bigger and bigger and bigger and faster over time. And then there's logistical growth, which is actual reality. When our population growth slows down and ends up stopping, okay, and there's no real positive nor negative growth, where it's reached what it's called our carrying capacity, okay, the total amount of individuals a population can grow.